Section 1.10, Applications of Linear Systems. The figure shows a network of 4 nodes in which the flow rate and direction of flow in certain branches are known. Find the flow rates and directions of flow in the remaining branches. How about we label the nodes A, B, C, and D. And then we could label the different rates x1, x2, x3, and it's already 15. Let's assign some directions to these flow rates. How about I make x1 go this way, x2 go this way, x3 go this way, and 15 has already been assigned. It doesn't matter if I got the flow rate direction wrong, because I'll just get a negative for the flow rate after I solve for it, and then I can correct the direction in the diagram. So by conservation of flow, the flows out have to equal the flow in for each of the nodes. So I must have that x1 plus x2 equals 30 for node A. Similarly, if I want to look at node B, the flows in, x2 and x3, must equal that 35 flowing out. So I'll have x2 plus x3 equal 35 at node B. For node C, my flows out are x3 and 15, so those must equal 60. So x3 plus 15 equals 60 for node C. And last but not least, for node D, we have x1 plus 15 equals 55. Okay, let's piece all these together. We've got x1 plus x2, leave a little space, equals 30. I've got x2 plus x3 equals 35. I've got x3 plus 15 is 60. It's the same thing as saying that x3 is 45. And over here, x1 plus 15 equals 55 is the same thing as just saying that x1 is equal to 40. Okay, so that gives me x1 must be 40. I know that x3 is 45, so that means that x2 must be negative 10. And like I said, x3 is 45. Okay, so now we know the flow rates. Because x2 is negative, that means that this flow rate, the direction of the flow, this arrow, is incorrect, and I should have drawn it going this way instead. The network in the figure shows a proposed plan for the traffic flow around a new park that will house the Liberty Bell in Philadelphia, Pennsylvania. The plan calls for a computerized traffic light at the north exit on 5th Street, and the diagram indicates the average number of vehicles per hour that are expected to flow in and out of the streets that border the complex. All streets are one way. How many vehicles per hour should the traffic light let through to ensure that the average number of vehicles per hour flowing into the complex is the same as the average number of vehicles flowing out? Okay, let's see. Flowing in, how about we write what that is? It looks like we've got 500, looks like we've got 400, 600, and 200 flowing in. So that's 500 plus 400 plus 600 plus 200 equals 1700 flowing in. All we did was just see that the arrow is pointing in for each of these. So now let's check flowing out. Well, we've got 700 flowing out. We've got, where is it, 400 flowing out. And it looks like we have whatever over here is at the traffic light flowing out, so we'll call that x. So flowing out, we have x plus 700 plus 400. Okay, so that means that if we want 1700 to equal this, we should just, well, notice this is 1100, so x must be 600. So that's how many vehicles per hour the traffic light should let in. Assuming that the traffic light has been set to balance the total flow in and out of the complex, what can you say about the average number of vehicles per hour that will flow along the streets that border the complex? Let's write out a little table. So I can list the intersections. I can list the flow in at each intersection. And I can list the flow out. So for A, let's see how much is flowing in. Here's A. It looks like in is 600 and 400, and out is x1 and x2. So in we've got 400 plus 600, and flowing out we've got x1 and x2. We want these to be equal. So that's the same thing as saying that x1 plus x2 should be equal to 1000. I'm leaving a little space because I'm going to have other variables pretty soon. So for intersection B, let's see, flowing in B, we've got x2 and x3. And flowing out, we've got x and 400. So x2 plus x3 should be equal to 400 plus x, which is the same thing as just saying that x2 plus x3 should be equal to 1000. Let's do intersection C now. In we've got 200, 500, and out we've got x3 and x4. So 500 plus 200 should be equal to x3 plus x4. So x3 plus x4 should equal 700. Okay, I'll do D. Looks like we have x4 and x1 flowing in, and we just have 700 flowing out. So x1 plus x4 should be equal to 700. Okay, so if we want to solve for each of these variables, let's see, we could take x1 and set it equal to 700 minus x4. We can set x2 equal to 1000 minus 700 minus x4. And we could set x3 equal to 700 minus x4. So we just use these two equations. Notice that in this case our x4 is our free variable. So how about we just make that some parameter t. So I'll say that x1 is 700 minus t, x2 is 300 plus t, x3 is 700 minus t, and x4 is just t. So this tells me that, well, remember that t, like all of the other cars flowing in the intersections, has to be greater than or equal to 0. So that means that the most that x1 could possibly be is 700, and the smallest it could be is 0. For x2, again, remember, t is greater than or equal to 0, so the smallest that x2 could be is 300. And the biggest it could be, well, let's see, what is the biggest that t could be? Well, if t is more than 700, then x1 would have to be negative, which it can't be. So that means that the most x2 could possibly be is 700 plus 300 is 1,000. And then for x3, we could see that it has to be greater than or equal to 0. Same as x1, and same as x1, it has to be less than or equal to 700. And then, like we said, t has to be at most 700, so we get the same restriction on x4. So notice this tells us the average numbers of the vehicles flowing along these streets that border, they have to be within these ranges. If a current of I amperes passes through a resistor with a resistance of R ohms, then there is a resulting drop of E volts in electrical potential that is the product of the current and resistance. That is, E equals I times R. Kirchhoff's current law states that the sum of the currents flowing into any node is equal to the sum of the currents flowing out. Kind of similar to the way we are applying the problems from before. Kirchhoff's voltage law states that in one traversal of any closed loop, the sum of the voltage rises equals the sum of the voltage drops. So how about we determine the current I in the circuit shown in the figure? We'll write E equals IR. In this case, we have our resistance is 3 ohms, so this is just 3I, because R is 3. Let's apply Kirchhoff now. Kirchhoff tells us that 3I must equal that 6, which means that I must be 2 amps. Notice I is positive, so we have the correct direction over here. The arrow is pointing in the correct direction. How about we determine the currents I1, I2, and I3 in the circuit shown in this figure? All right, a little more complicated. Let's make a table like we did in example 2. So I'll write out my nodes. I'll write the current going in. And I'll write the current going out. Okay, for node A, we have the current going in is I1 and I2, and the current going out is I3. So I1 plus I2 has to equal I3. For node B, we have that the current going in is that I3, and the current going out, in this case, are that these guys, I1 and I2. Okay, so that tells us that, it's supposed to be an arrow, I1 plus I2 minus I3 has to be 0, right? I'll just subtract I3 from either side of these equations. Okay, how about we make another table that shows the voltage rising and the voltage dropping. So I've got my voltage rises, my voltage drops, and I'm going to look at the left inside loop, my right inside loop, and my outside loop. So first let's do the left inside loop. Okay, so looks like on the left, my voltage is rising 50, and it's dropping 5I1, and it's dropping 20I3. So it's rising 50 and dropping 5I1 plus 20I3. Okay, how about for the right inside loop? Okay, for the right inside loop, it looks like my voltage is rising 30 plus 10I2 plus 20I3. So I get 30 plus 10I2 plus 20I3. And it doesn't look like the voltage is dropping at all. How about for my outside loop? Okay, for my outside loop, it looks like I go 30, 50, and 10I2, and I drop 5I1. Okay, so we got 30 plus 50 plus 10I2, and we drop 5I1. Okay, so that means that if I combine all these facts together, we get 5I1 plus 20I3 is equal to 50. I get 10I2 plus 20I3 is equal to negative 30 by just subtracting 30 from the other side. And I get 5I1 minus 10I2 equals 80 by collecting like terms. Okay, so let's see if we can solve this. We've got I1 plus I2 minus I3 equals 0. From over here, we've got 5I1 plus 20I3 equals 50. And we've got 10I2 plus 20I3 equals negative 30. I'm not going to bother with this equation on the bottom because it's just the difference of the first two equations. If you take this minus this, you get the last equation, so it doesn't add anything to our system. So now I'll solve the system I do have by writing the coefficients 1, 1, minus 1, 0, 5, 0, 20, 50, 0, 10, 20, minus 30. Okay, so that becomes 1, 1, minus 1, 0, 0, minus 1, 5, 10. I'll just subtract 5 of this from this one to get a 0 underneath. And I already have a 0 over here, but I could take 10 of these guys and add it to this to cancel out this 10, so I can get a 0 underneath this in anticipation of making that into a leading 1. So I'll get 0, 0, 7, 7. And then I'll get a 0 above over here. So I will add this row to this row, second row to my first. So I'll get 1, 0, 4, 10. And I'll multiply my second row by -1 to get 0, 1, -5, -10. Now I have a leading 1 there. And my last row I'll divide by 7 to get 0, 0, 1, 1. Okay, last but not least, I'd like to get zeros over here. So I will just add multiples of this row to my first and second. I'll get 1, 0, 0, 6. I'll get 0, 1, 0, -5, and 0, 0, 1, 1. Okay, great. So now this is in reduced row echelon form. It's actually identity. So that means that I1 is equal to 6, I2 is equal to -5, and I3 is equal to 1. Let's do a chemistry example. How about we try to balance this chemical equation? So to balance it, we need to come up with coefficients that make it so that we have the same number of atoms on each side. So notice over here we have 3 sodium atoms, and over here we only have 1. So right now it's not balanced. So we need to come up with some multiple for each of these molecules. So how about x1 for the hydrochloric acid, x2 for the sodium phosphate, x3 for the phosphoric acid, and x4 for the sodium chloride. And I'll just try to find out what the x1, x2, x3, x4 are that'll make this equation balanced. So looking over here and collecting each of my atoms, I've got 1 x1 hydrogen left. So 1x1 should be equal to 3x3, because notice there's 3 hydrogens over there. So that gives me the coefficient 3 for my coefficient x3. That's for my hydrogen. Let's do chlorine next. So we've got 1x1, and there's only 1 chlorine on this side, so that should equal 1x4. Okay, let's do sodium now. We've got 3 sodiums over here, so it should be 3x2 from that. And on the right, we've only got 1, so it equals 1x4. Okay, how about for the phosphorus? We've only got 1, so 1x2 should be equal, let's see, phosphorus on the right is only 1, should equal 1x3. Then oxygen, we've got 4, so 4x2. And on the right, we've got 4, so 4x2 should be equal to 4x3, oxygen. Okay, so let's write a system of equations. We've got 1x1 minus 3x3 equals 0, x1 minus x4 equals 0, 3x2 minus x4 equals 0, x2 minus x3 equals 0, and 4x2 minus 4x3 equals 0. So my matrix would be 1, 0, minus 3, 0, 0, 1, 0, 0, minus 1, 0, 0, 3, 0, minus 1, 0, 0, 1, minus 1, 0, 0, 0, 4, minus 4, 0, 0. And I'm going to take that and try to reduce it. So how about I write 1, 0, minus 3, 0, 0. Just keep my first row, it already has a leading 1. I need to get rid of that 1 over there, so I'll just subtract the first row from it. And I'll get 0, 0, 3, minus 1, 0. I'll divide this row by 3 so I can get a 1 over there, and I'll move it later. So I'll get 0, 1, 0, minus 1/3, 0. And I will get rid of this 1 over here, subtract 3 of this guy. So, or just subtract this guy over here, if you like that better. So 0, or by 3 I meant 1/3, 0, 0, minus 1, 1/3, 0. And then my last row, notice, is just a multiple of this one. So I could just add a multiple of this one to it to cancel it out. So I just get zeros. That shouldn't be surprising from the very beginning. We saw if 1x2 equals 1x3, it's the same thing as saying 4x2 equals 4x3. It's redundant. Okay, so how about I move this row up? So I'll keep my top row, 1, 0, minus 3, 0, 0. My second row will become 0, 1, 0, minus 1/3, 0. And then I could just multiply that by minus 1. So I'll get 0, 0, 1, minus 1/3, 0. Notice this row is a multiple of this one, so I can cancel it out, just get zeros. And I still have zeros in the bottom. Okay, I just have to get rid of this minus 3, so I'll just add 3 of these. So I get 1, 0, 0, minus 1, 0, 0, 1, 0, minus 1/3, 0, 0, 0, 1, minus 1/3, 0, and then all zeros. Okay, so that tells me, since I have 2 rows of zeros, I have a whole bunch of options when it comes to balancing this chemical equation, because these 3 variables will be explicitly defined in terms of my free variable x4. So I'll get x1 equals x4, which I can call t, x2 equals t over 3, x3 also equals t over 3, because just take the this guy and just move it to the other side. So if x2 is 1/3 of x4, it's the same thing as just, x4 over 3 is t over 3. x4 would just make t our parameter. So I would like to have something that's not a fraction for these coefficients. So it looks like the smallest I could make t to eliminate the fraction over here, make it cancel, would be 3. So I'll just set t equal 3, and I'll get x1 equals 3, x2 equals 1, x3 equals 1, and x4 equals 3. And notice any multiple of 3 would have helped balance this equation. So my equation ends up as 3HCl plus Na3PO4 yields H3PO4 plus 3NaCl. And you can double check that there are the same number of atoms on each side. Polynomial interpolation. Given any endpoints in the xy plane that have distinct x-coordinates, there is a unique polynomial of degree n-1 or less whose graph passes through those points. As an example, let's find a cubic polynomial whose graph passes through these 4 points. So just to write a general polynomial, I'll let p of x equal a naught plus a1x plus a2x squared plus a3x cubed. That's a general cubic. It looks like I've got x1 equal 1. That's my first corner over there. x2 is equal to 2. x3 equals 3. And x4 equals 4 are my 4 x values. My 4 y values are y1 equals 3, y2 equals -2, y3 equals -5, and y4 is equal to 0. So let's make a little matrix out of this. This tells me I've got 1 x1, x1 squared, x1 cubed, and y1. If I were to plug in my first point, x1 and y1, into my polynomial, this might seem a little strange because usually we write the matrix having the coefficients of our equation, and you would think, okay, that's a1, a0, a2, a3, but in this case, that's what we want to solve for. Those are unknown values. The coefficients are 1, x, x squared, x cubed, and it equals y. So I'm going to get an equation for y1, and an equation for y2, an equation for y3, and an equation for y4, and putting all of those together, I can solve for a0, a1, a2, a3. So that's what I'm not going to write, because that's what I'm trying to solve for. I'm just writing the coefficients of a0, a1, a2, a3. So for my second equation, that's just y2. My third one is for x3 and y3. And for my fourth one, it's just x4 and y4. Okay, so there's my matrix. I want that to equal the values that I chose, so I'll just plug those in, or the values I was given. So 1 stays 1, x1 is just 1, x1 squared is just 1, x1 cubed is just 1, and y1 was 3. Okay, then x2 was 2, 2 squared is 4, 2 cubed is 8, and then it has to equal -2. Then for x3, that was 3, 3 squared is 9, 3 cubed is 27, and that has to equal -5. And x4 was 4, which is squared gives me 16, and cubed gives me 64, and that has to equal y4, which is 0. Okay, so let's try solving this system. Let's leave the top row the same because it already has leading 1, so 1, 1, 1, 1, 3. My second, third, and fourth rows, I'll subtract the top row to get zeros. So I get 0, 1, 3, 7 minus 5, 0, 2, 8, 26 minus 8, 0, 3, 15, 63 minus 3. Okay, I got a leading 1 there. I just need to get zeros over here, so I'll subtract 2 times the second row from the third and 3 times for the fourth one. So I'll stick with 1, 1, 1, 1, 3 up top. I'll stick with 0, 1, 3, 7 minus 5 for my second row, but I'll get 0, 0, 2, 12, 2 for my third, and 0, 0, 6, 42, 12 for my fourth row. Okay, let's continue. Making good progress. I'll keep my top row, 1, 1, 1, 1, 3. I'll keep my second row, already has leading 1, 0, 1, 3, 7 minus 5. Then my third row will divide by 2. I'll get 0, 0, 1, 6, 1. And then for my fourth row, I'll subtract 6 of my third row to get 0, 0, 0, 6, 6. And then that becomes 1. I want to get a 0 over here, so I'll subtract my second row. So I'll get 0 minus 2 minus 6, 8, 0, 1, 3, 7 minus 5, 0, 0, 1, 6, 1, and 0, 0, 0. Divide by 6, we get 1, 1. Okay, how about we get zeros over here now? So I'll subtract multiples of my third row. So I get 1, 0, 0, 6, 10, 0, 1, 0, negative 11, negative 8, 0, 0, 1, 6, 1, and 0, 0, 0, 1, 1. Okay, almost done. I just need to get zeros over here. So I'll just subtract multiples of my fourth row, or add for this guy, and I'll get 1, 0, 0, 0, 4, 0, 1, 0, 0, 3, 0, 0, 1, 0, minus 5, 0, 0, 0, 1, 1. There we go. Okay, so we finally solved this thing because we put it in reduced row echelon form. We see that a 0 must equal 4, a 1 must equal 3, a 2 must equal negative 5, and a 3 must equal 1. So that means my polynomial is p of x equals 4 plus 3x minus 5x squared plus x cubed. So if I want, I could do a little graph, show you what this looks like. So here's my x-axis, here's my y-axis, here's 1, 2, 3, 4. And here's minus 1, 1, 2, 3, 4. Here are my points. Oh, I need some negatives. Do negative 1, negative 2, negative 3, negative 4, negative 5. So here's a point. Here's my next point. Next point. Last point. And I need a nice cubic polynomial that cuts through these guys. Looks something like this. Pretty cool. How about we use polynomial interpolation to approximate this integral over here? So, because remember, some integrals are pretty difficult to calculate, but can be approximated, a little bit more easily. So let's set x0 equal to 0. Let's see. It looks like I need a couple more values they didn't give me. I'm going from 0 to 1. So how about I break this thing up into 5 different values? I could choose 3 in between. So I'll break it into quarter chunks. So I'll do x1 equals 0.25, x2 equals 0.5, x3 equals 0.75, and x4 is 1. So because I'm going up to x4, I should anticipate a 4th degree polynomial will approximate this, which should be a pretty good approximation, right? Okay, let's see. I'll take f of x equals sine of pi x squared over 2. F of 0 is just 0. F of 0.25 is 0.098017. F of 0.5 is 0.382683. F of 0.75 is just 0.77301, and f of 1 is 1. That's just what you get by using a calculator for the integrand. So I will make a table similar to the last example with my, I don't have 5 rows this time because I have 5 different x values, because remember I have these 4, but then I also have x0. So I'll get, remember it's a0 plus a1 times x, and so on. So I'm doing the coefficients of all the a's. So the coefficient of a0 is just 1. The coefficient of a1 is just going to be my first x, x0, and so on. So I'll have x0 squared, x0 cubed, x0 to the 4th, and f of x0 is my y value. That's my first possibility. Then I get another equation for x1. I get another equation for x2. So x2 squared, x2 cubed, x2 to the 4th, and f of x2. Then for x3, and last but not least for x4. So x4 squared, x4 cubed, x4 to the 4th, and f of x4 is my last y value. Okay, so that's my matrix. What I'm going to do is I'm going to plug in all of the values that I already got. So it gives me 1, 0, 0, 0, 0, 0 for x0, then 1.25 for x1, 0.25 squared, 0.25 cubed, 0.25 to the 4th, and 0.098017. Same thing for 0.5, 0.5 squared, 0.5 cubed, 0.5 to the 4th, and that should equal 0.382683. Then 0.75, 0.75 squared, 0.75 cubed, 0.75 to the 4th, and I should get 0.77301. And then 1 squared, cubed, etc. is all just 1. Okay, so then if I painstakingly take this matrix and put it in reducer echelon form, I'm not going to actually do it by hand. You could use a calculator. I'm going to get 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0.098796, 0, 0, 1, 0, 0, 0.762356, then 0, 0, 0, 1, 0, 2.144288, and 0, 0, 0, 0, 1, negative 2.00544. So plugging that into my polynomial equation, I get that an approximating polynomial is 0.098796. That's x. Notice there's 0 for my constant value, plus 0.762356x squared, plus 2.144288x cubed, minus 2.00544x to the fourth. And if I integrate that polynomial, which is much easier than integrating this original function, I can just do that way more easily, and I'll get roughly 0.438501. Remember, you just do x squared over 2, x cubed over 3, x to the fourth over 4, x to the fifth over 5th, evaluated at 1. You won't need to evaluate at 0 because when you subtract off, 0 will kill all these guys. So it's a pretty easy integral to do compared to this very difficult integral. Oh, and I forgot to put my brackets for my matrix over there. Notice also that if we were to graph this thing, it looks something like this. And I can approximate by just taking a bunch of points. Let's say this is at 0.5, and then this is at 1. And let's say this is 0.25, 0.5, and okay, over here we can make that 1, so I'll have to squeeze in 0.75. Not the best drawing, but we'll make do. So then I got a point over here, point over here, point over here, point over here. If I were to look at the approximating polynomial, it would look something like this. It's a pretty good approximation for the most part.